Somewhere right now, inside a building at NASA's Jet Propulsion Laboratory in Pasadena, California, a small team of engineers is preparing to attempt something they have never done before on the most distant machine humanity has ever built. Not a new spacecraft, not a mission that launched last year, a machine that left Earth in 1977, before the internet existed, before home computers existed, before most of the people currently monitoring its systems were even born. They call the procedure the Big Bang, not because it's elegant, not because it's a poetic nod to the origin of the universe. They call it that because of what it actually involves. A single, simultaneous, all-at-once reconfiguration of how electrical power flows through every remaining active system on the spacecraft. Not one system at a time. Not a careful, sequential shutdown and restart where you can pause and check your work. Everything all at once, in one coordinated swap, attempted from a distance of more than 16 billion miles, through a communication loop where every single command takes about 23 hours just to arrive. And another 23 hours for the response to crawl back to Earth. One attempt, one window, no second chances. If it works, the spacecraft could keep operating for several more years, possibly even bringing a permanently shut down science instrument back online. If it fails, it could push a machine that has already outlived its 5-year design life by nearly 10 times into silence, permanently, with no way to send a repair crew, no way to send a replacement part, no way to do anything except watch the data stop arriving and know that after 49 years, humanity's furthest reaching conversation with the universe has ended. This is the story of Voyager 1. And what's happening to it right now, in the middle of 2026, is not science fiction. It's not a headline written to scare you. It is an actual, real, currently unfolding decision being made by actual engineers, about an actual machine with actual stakes, and almost nobody outside the space community is talking about it. By the end of this video, you'll understand exactly why this gamble had to happen, what could go wrong, and why the answer to whether it worked won't arrive for months. To understand why NASA is willing to take this kind of risk, you have to understand what Voyager 1 actually is, and what it has already survived. Voyager 1 launched on September 5th, 1977 at 8:56 in the morning, Eastern Time, lifting off from Cape Canaveral atop a Titan IIIe Centaur rocket. It wasn't originally supposed to do any of this. Its mission was to study Jupiter and Saturn, and it was designed to operate for about 5 years. That was the plan. Fly past 2 planets, gather data, and quietly become a piece of space history drifting silently through the dark. Except the outer planets happened to be aligned in a way that wouldn't repeat for another 175 years. A rare gravitational arrangement that let engineers use each planet's gravity like a slingshot, picking up speed, and redirecting course without burning a single extra drop of fuel. NASA had actually dreamed of an ambitious, grand tour of all 4 outer planets, but budget cuts scaled that vision down. Still, Voyager 1's trajectory past Saturn's giant moon Titan in November 1980 tilted the spacecraft up and out of the plane of the solar system entirely, ending its planetary tour, but sending it on a one-way path toward the stars that nobody had originally planned for. Along the way, it made discoveries that rewrote textbooks. At Jupiter in March 1979, it revealed active volcanoes on the moon Io, the first time volcanic activity had ever been observed anywhere beyond Earth. At Saturn in November 1980, it captured unprecedented close-up detail of the planet's rings and its giant moon Titan, showing scientists for the first time that Titan was wrapped in a thick, hazy nitrogen atmosphere. Then, in 1990, at the direction of astronomer Carl Sagan, the spacecraft turned its camera around and took one final photograph looking back at Earth from about 6 billion kilometers away. In that image, Earth appears as nothing more than a tiny speck of light caught in a scattered sunbeam. Sagan would later describe it as a way of understanding just how small and fragile our home really is in the vastness of everything else. That photograph, the pale blue dot, became one of the most quietly powerful images ever taken. Not because of what it showed, but because of what it didn't. Just us. Just 1 pixel. After that, NASA extended the mission under a new name, the Voyager Interstellar mission, with a new, far stranger goal. Keep going and find out what actually exists at the edge of the sun's influence and beyond it. On August 25th, 2012, Voyager 1 crossed something called the heliopause, the invisible boundary where the constant outward pressure of the sun's solar wind finally gives way to the pressure of the material between the stars. It became the first human-made object in history to leave the bubble of our own solar system and enter true interstellar space. Voyager 2 followed in November 2018, taking a different route out. Today, both spacecraft are still out there, still transmitting, still the only 2 machines ever built that can tell us what interstellar space actually feels like from the inside. But that survival has come at an enormous cost, and the cost is power. Voyager 1 doesn't have solar panels. This far from the sun, sunlight is far too weak to be useful. Instead, both Voyagers run on something called a radioisotope thermoelectric generator. a device that converts the heat given off by decaying plutonium into electricity. At launch, that system produced about 470 watts. Today, it produces somewhere around 250 watts. And it keeps declining by roughly 4 watts every single year, with absolutely no way to refuel it, ever. Of the 10 identical sets of scientific instruments each Voyager originally carried, engineers have now been forced to permanently shut down 7 of them, one at a time, over the decades, purely to conserve enough electricity to keep the spacecraft's heaters running, its antenna pointed at Earth, and its remaining instruments alive. This wasn't a decision made in a panic. Years ago, the Voyager science and engineering team sat down together and agreed, in advance, on the exact order in which they would sacrifice each instrument, prioritizing whichever data was most scientifically irreplaceable for as long as possible. In April 2026, the next name came up on that list, the Low Energy Charged Particles Instrument, known as the LECP. It had been running almost continuously since 1977, nearly 49 years, measuring the ions, electrons, and cosmic rays drifting through the solar system and, later, through interstellar space itself. It was this exact instrument that helped confirm, back in 2012, that Voyager 1 had truly crossed into the space between the stars. The shutdown wasn't planned for that particular moment either. During a routine, pre-scheduled roll maneuver on February 27, 2026, Voyager 1's power levels dropped unexpectedly. Engineers realized that any further decline could trigger the spacecraft's built-in undervoltage fault protection system, an automatic safety mechanism that would begin shutting down components on its own without human input to protect the probe from a total power failure. Recovering from that kind of automatic shutdown is a long, risky process in itself. So instead of waiting to see what the spacecraft might do on its own, the team decided to act first, deliberately, on their own terms. As Kareem Badarudin, Voyager's mission manager at JPL, put it in an official NASA statement, shutting down a science instrument is not anybody's preference, but it is the best option available. Voyager 1 now has exactly 2 operating science instruments left, one that listens to plasma waves and one that measures magnetic fields. That's it, out of an original 10. And that is precisely why the Big Bang is being attempted at all. Let's talk about exactly how far away and exactly how fragile this conversation actually is. Right now, Voyager 1 sits at a distance of roughly 25, 9 billion kilometers from Earth, about 16, 1 billion miles. To put that into some kind of perspective, light itself, moving at 300,000 kilometers every single second, takes about 23 hours to cross that distance, not minutes, not an hour. The better part of a full day, one direction. At the fastest speed anything in the universe is physically allowed to travel. That means every single command NASA sends to Voyager 1 takes roughly 23 hours just to arrive. And then, if the spacecraft responds, that response takes another 23 hours to crawl all the way back to the giant dish antennas of NASA's deep space network here on Earth. Voyager mission manager Susie Dodd once summed up what that actually feels like in practice. If she sends a command and says, "Good morning, Voyager," on a Monday morning, she won't hear its answer until Wednesday morning. Think about what that means for troubleshooting. If something goes wrong during the Big Bang procedure, engineers won't know about it in real time. They won't be able to react in the moment, adjust on the fly, or send a quick correction. They will send a command into the dark and then simply wait 2 full days to find out whether it worked, whether it partially worked, or whether it went catastrophically wrong. There is no other machine humans have ever operated where the feedback loop is measured in days instead of seconds, and in November 2026, that gap is about to become even more staggering. Around November 15th to 18th, depending on which tracking calculation you use, Voyager 1 will cross something no human-made object has ever reached before. 1 full light day from Earth. At that point, it will be traveling at around 61,000 kilometers per hour, or about 38,000 miles per hour, continuing to pull away from us by roughly that same distance every single hour, forever, with no way to slow down or turn back. Meanwhile, the spacecraft itself is a genuine relic. Its 3 onboard computers share a combined total of just 68 kilobytes of memory, less than a single low-resolution photo on a modern phone, running on processors clocked at only 250 kilohertz. Commands are transmitted up to the spacecraft at a mere 16 bits per second. Scientific data comes back down at roughly 160 bits per second. For comparison, that is slower than a fax machine from 1985. And yet, across that impossibly thin, impossibly slow trickle of information, traveling across more than 25 billion kilometers of empty space, Voyager 1 continues to send back real, usable, scientifically valuable data about a region of the universe that no other instrument humanity has ever built can currently reach. Every watt matters. Every heater left running risks freezing critical fuel lines in a place where the ambient temperature sits at roughly minus 270 degrees Celsius, barely above absolute zero. Every science instrument left on draws power away from the systems that keep the spacecraft's antenna precisely pointed at a planet it can no longer see, aimed with pinpoint accuracy across a gap of more than 16 billion miles. Turn off too little, and the spacecraft freezes. Turn off too much, and it goes deaf, mute, or simply stops working entirely. This is the tightrope Voyager engineers have been walking for nearly 3 decades now, quietly, one instrument and one heater at a time, extending a 5-year mission into a 5th decade through nothing but careful math and difficult sacrifices. And now, for the first time, they're not just turning things off one at a time anymore. They're about to flip the entire power architecture of the spacecraft all at once, in a single unified move. And they're doing it because the slow, careful approach has finally run out of easy options. So what exactly is the Big Bang? In simple terms, it's a complete simultaneous rewiring of how electrical power is distributed across every remaining active system on the spacecraft, swapping older, more power-hungry components for lower power alternatives, all activated together in one coordinated sequence rather than one careful step at a time. Engineers believe this single move could free up enough power to keep each spacecraft's 2 remaining instruments running for roughly another year beyond where they'd otherwise have to shut something else down, and possibly even allow the freshly deactivated LECP instrument on Voyager 1 to be switched back on. But a maneuver like this, executed all at once across nearly 50-year-old hardware, is not something you get to test twice. So NASA made a calculated decision. Attempt it first on Voyager 2. Voyager 2 was chosen deliberately, not randomly. It currently has slightly more spare power available than its twin, and it sits closer to Earth, roughly 21, 35 billion kilometers away, compared to Voyager 1's 25, 4 billion. Both of those factors make it the comparatively safer test subject. If something goes wrong on Voyager 2, the mission still has Voyager 1's data. If something had gone wrong on Voyager 1 first, there would be no backup. Testing on Voyager 2 was scheduled for May and June of 2026. If those tests succeeded, the plan was to attempt the exact same procedure on Voyager 1 no earlier than July 2026. And if it works there too, there's even a possibility that Voyager 1's LECP instrument, the one shut down back in April, could get a second chance to keep collecting data from a region of space no other instrument has ever explored. This is, quite literally, happening on the timeline we're in right now. As of this video, the Voyager 1 attempt is expected to take place no earlier than July 2026, which means somewhere in the coming weeks, a decision that has been years in the planning is finally reaching the moment where it either works or it doesn't. Consider what's actually being asked of this hardware. This is a spacecraft built with 1970s era engineering, designed by people using slide rules and hand calculations decades before anyone imagined a simultaneous power reconfiguration would even be a phrase anyone needed. Every wire, every relay, every switch on Voyager 1 has been operating continuously in the punishing cold and radiation of deep space for nearly half a century, with zero opportunity for physical maintenance, repair, or replacement. And now engineers are asking that same half-century-old hardware to execute a completely new kind of command it was never specifically designed to run, one single unified action on the first and only try, from a control room over 16 billion miles away. If it succeeds, Voyager 1 potentially gets more time, more data, more distance, more of that one-of-a-kind window into interstellar space that nothing else humanity has ever built can currently provide. If it fails, the most likely outcomes range from losing an instrument permanently to triggering exactly the kind of automatic protective shutdown the team has spent years trying to avoid. A scenario that could take an already fragile, aging spacecraft and push it into a diminished, uncertain state from which full recovery may not be possible. There's no rehearsal for this. There's no simulator that perfectly replicates 49 years of accumulated wear on a real spacecraft flying through real interstellar radiation. The only true test is the real one. And by the time anyone on Earth even knows whether the Voyager 1 attempt has begun, another 2 days will have already passed in near total silence. It's worth pausing here to ask a simple question. Why does any of this actually matter? Why go to these lengths, take this level of risk, over one aging spacecraft that has technically already completed its mission several times over? Because Voyager 1 and Voyager 2 are not replaceable. Not this decade, not this generation. They are the only 2 spacecraft that have ever operated in true interstellar space, the region beyond the protective bubble the sun's solar wind creates around our entire solar system. Every reading they send back about magnetic fields, plasma density, and cosmic ray activity in that region is, right now, in 2026, still the only direct, real-world data of its kind that exists anywhere. There is no backup satellite quietly collecting the same information. There is no faster mission already out there, ready to take over the moment Voyager goes silent. When these two machines eventually stop transmitting, whether that happens gradually over the next few years or abruptly during a moment exactly like this one, humanity's direct connection to that region of space goes with them for however long it takes to build, launch, and fly a replacement mission that far, likely a matter of decades. And there's something else worth sitting with. Bolted to the side of each spacecraft is the golden record, a gold-plated copper disc containing greetings recorded in 55 different languages, music sampled from across human history and culture, scientific diagrams explaining who and where we are, and a map showing Earth's position relative to a set of nearby pulsars. It was assembled by a team led by Carl Sagan, intended as a kind of message in a bottle, cast into an ocean so vast that the odds of anyone ever finding it are almost impossible to calculate. That record will keep traveling outward with the spacecraft, silently for millions or even billions of years, long after Voyager's instruments have gone quiet, long after the last engineer who ever worked on this mission is gone, long after Earth itself has changed in ways none of us can predict. Whether or not the Big Bang succeeds this July won't change that. The golden record keeps moving either way. But whether Voyager 1 keeps talking to us while it does, whether we get one more year or several more years of real data from the edge of everything we understand, depends entirely on whether a single, all-at-once power gamble works correctly, the first time, on hardware that has already outlived every original expectation anyone ever had for it. So here's where things actually stand right now, as you're watching this. Voyager 2's version of the Big Bang was scheduled for May and June of 2026. Voyager 1's attempt is expected no earlier than July 2026. Depending on exactly when you're watching this video, that attempt may already be underway right now, 16 billion miles away, in complete silence, with the outcome still more than 2 full days away from being known to anyone on Earth. And regardless of how that gamble turns out, Voyager 1 is still on track to cross its 1 light day milestone in mid-November 2026, a distance so vast that describing it in miles or kilometers barely does it justice anymore. At that point, saying good morning to Voyager 1 and getting an answer will take a full 2 days, round trip, guaranteed forever, for as long as the spacecraft keeps functioning. The real question isn't whether Voyager 1 still has secrets left in the dark between the stars. 49 years of data has already proven that it does, again and again in ways that have forced scientists to revise their models more than once. The real question is simpler and far more human. Can a spacecraft built almost 50 years ago, using hardware nobody living today would ever choose to rely on, survive one more all-or-nothing decision made from a control room more than 16 billion miles away? We don't know yet. Nobody does. Not NASA, not the engineers who designed the procedure, not anyone watching the data come in. The signal is still on its way. The only thing we can do now is wait and listen. If you want to be here the moment NASA confirms exactly what happened, whether the Big Bang succeeded on Voyager 1, whether the LECP instrument comes back online, or whether the team has to make an even harder decision next, subscribe to the channel and turn on notifications, because the moment that update lands, we'll be breaking it down here, in full, with the real data, not the invented version. One machine, 4 watts and falling, 16 billion miles. One chance to get this right. Thanks for watching.